I haven't checked the voice actually on this, but
No, it's okay.
is that okay? This work? Good.
Right. Welcome again to another edition of the CSP seminar. As some of you know, we have started re-inviting some of our alumni since the last semester. We had Henderson and Shao, and we're continuing with Murat and so just by way of introduction, for those of you who are Murat came to us in '94, which is a little before I joined CLSP. I think Fred had just got in here and Fred was instrumental in recruiting him into us to build him. And he finished in 2000 with a PhD, with some really nice work in pronunciation modeling, and has since then been at Unity Labs. He's with the multimedia group. I think specifically the division that he's in is called Speech-Enabled Services. But like a lot of people in the GP, he works on these various aspects of the communication problem. And today he's going to talk to us about some of the more recent work on this particular language.
Thank you, Sanjeev. Yeah, it's good to be home, away from home, I guess. Seeing old faces and new faces as well. I'll be talking about discriminative language modeling work that we did jointly with Brian Rourke, who is still at AT&T, but will be at OGI, as I was saying, and Michael Collins, who was at AT&T when we first started, and who is now with MIT AI Lab. And this is also in collaboration with Mark Johnson from Brown and Nikki Albakiani. And so here's the overview of the talk. I'll basically give the motivation, and my motivation is going to be very clear actually, but and some related work dating back to actually Fred's ideas, and some background on linear models, which are our instrumental tool here, and use of weighted finite state automata. And the first algorithm I'm going to talk about is the well-known, actually, perceptron algorithm. I'll give experimental results both on switchboard and some other corpora that I'm going to explain. And finally, an improvement on the first system will be presented, which is based on the idea of conditional random fields. And again, the results on switchboard will be following. So, well, recent years have seen great improvements on larger vocabulary ASR using discriminative techniques for acoustic modeling. Actually, discriminative techniques have been around for a while, but showing that they're effective in large vocabulary only appeared in the last 5 years or so with lattice-based techniques in Cambridge University, from Cambridge University. And it's now in almost all state-of-the-art acoustic modeling systems. Most of the evaluation systems have state-of-the-art lattice-based, either maximum mutual information estimation or conditional maximum likelihood estimation in part. But this is not the case for language modeling. I mean, there's no discriminative language modeling that is being used generally in these state-of-the-art systems. And n-gram models have been around forever, and they're still the state-of-the-art. And we can efficiently represent n-gram models with weighted finite state automata. And actually, at AT&T, we're using finite state automata and transducers in all of our recognizers and ASR systems. So we want to be staying in the same framework of using n-grams and models that are representable as finite state automata, but we want to be estimating our models discriminatively. So parameter estimation, we want to be discriminative, and the lattice-based part is going to be one of the key issues. So related work, oops. Okay. Basically, Fred had this research report titled Acoustic Sensitive Language Model in maybe '95, which had the idea of minimizing the entropy of the word string given the acoustic string. And Stolke and Weintraub had tried various approaches, including MMIE in language modeling. But this had mixed results and didn't really seem to improve anything. Stolke later on in 2000 had this idea of an anti-language model, which basically has the usual language model component estimated from the transcriptions, but also has this negative contribution from the n-best output. So the positive evidence and the negative evidence coming from the wrong hypotheses, if you will. Some people from MSR China, Microsoft Research at China, this idea of changing the trigram counts as well as the lexicon discriminatively. Basically, as they make mistakes, they discount the counts, and as you get more evidence, you increase the counts. And that has some similarities, but it's actually very different because the lexicon keeps changing as well. And finally, Jeff Kuo, Eric Foster, and others at Bell Labs had some implementation of string error minimization, basically classification error minimization based on generalized probabilistic descent algorithm. And they tried this on DARPA communicator task, which was middle vocabulary, and they had mixed success there as well. It wasn't very robust, basically. And in 2002 evaluation for switchboard, our system actually had something that Michael Collins had started, which used boosting to estimate parameters of a rescoring model. So the idea is, that in the first pass, we generate lattices. We use a rescoring language model, which has different parameters, which will choose the best hypothesis in terms of minimum sentence error rate again. But it is trained using boosting discriminatively. And unfortunately, although this system gave good results in development, at test time it was not very good. And we wanted to understand why and basically work on it more and improve the machine learning algorithms behind it. And this is what basically started this work 2 years ago or so. But we stopped soon after, and Michael had left. But we started last year again with Brian and actually solved most of the problems. And I'm going to be talking about these and the improved results as well. All right, the underlying model can be named in different ways. We're calling it linear models, starting from Michael Collins' work. Basically, it is equivalent to what we will call exponential models later in the talk, or log linear models. The idea is we are trying to learn a mapping from inputs x to outputs y. In our case, this is basically x is the utterance, so the acoustic signal, and y will be the transcription. So we're going to assume training examples for xi, yi pairs. A function gen, which actually comes from the optimality theory literature. Basically, that gives a set of candidates, gen x for the input x. In our case, this is the baseline recognizer, and gen x is actually the word hypothesis represented in the lattice, so the first pass output. Then there is the representation, which has a set of features, mapping each xy pair to a feature vector in the d-dimensional real space. And this representation is basically the n-gram counts in our case. I'm going to explain it a little bit more. And there's a parameter vector, alpha, which multiplies this representation vector. And the linear part comes from this simple multiplication. There's a linear relation. So for n-grams in our case, the feature vector for a given transcription y of the utterance x is basically the n-gram counts up to length 3 in our case. So unigrams, bigrams, and trigrams in a certain string, we have the counts represented as a vector. And in addition, we have the baseline recognizer score. So since this is a rescoring model, we have the initial score also represented as a feature, and there will be a multiplier to that, which is the parameter for the baseline score. And most of the algorithms that I'm going to explain are actually based on simple algorithms that are implemented in the AT&T FSM library, as well as the new GRM library. So one functionality is this GRM count, which is able to count from weighted lattices these n-grams. So unigram, bigram, trigram counts in a lattice. They can be fractional, because these are all probabilistic weighted automata. And other improvements on the simple finite state framework. I'll be talking about the failure class, which is an efficient way of representing back-off models. Which was
just to be clear,
yeah.
Phi of xy
Yes.
let's say you allow the case of all n-grams up to length 3, then it's the dimension of 3 is basically v plus v squared plus v cubed.
Yeah, conceptually it is like that, yes, yes. So I'm going to be talking about the number of parameters, and then we will be basically focusing on those things that are non-zero. So all the zero parameters are going to stay the same.
It might be very sparse, but that's essentially the dimension.
That is the conceptual dimension, yes. You can actually restrict it from the beginning, but as we're going to see, the perceptron algorithm actually chooses things. So let me just explain how we're doing the counting before I go any further, because that is nice to understand. So given an arbitrary weighted automata over any simmering actually, but we're going to talk about probability simmering here. If the automaton is deterministic and pushed so that we're defining a probability distribution, then the weight is essentially that probability of any string given the lattice. So what we're producing here is the posterior distribution over the paths that are contained in the lattice, given the lattice. So the probability mass is going to be 1, and it's renormalized. So we define the count of any sequence x in the automaton as this formula, basically, where we have the weight, essentially the probability of a certain path, and the number of times the substring x appears in the path u. And this can be actually computed in a very simple way. Yeah.
Just get the notation straight.
All right.
So u is a string of words in reality?
Yeah, u is a string of words, or it's a path in the lattice. It's the same thing.
Well, okay,
yeah.
So it's a string of words.
Yes.
And u, absolute value sub.
Right, this part.
Yes, is what?
Is the number of occurrences of this x, which is a substring of u, in u. So it might be a unigram. Just think of
so
a unigram.
Normally it would be marked as some kind of a sum of delta function.
Yes, that is exactly what it is, yeah.
I just don't know this notation.
Oh, okay, okay. Well, this is what basically Meriar used in the GRM library, and that's stuck, basically. So, yeah.
And sigma star
sigma,
yeah. It's not everything. It's just what's in the lattice.
That is correct. That is correct. That is correct. But since probability distribution outside the lattice is basically 0, you can think of it as the sigma star of the usual sense. So it's equivalent.
In that case, A of u for u outside is 0.
Yes. Yes.
You're counting overlapping occurrences twice.
Sorry?
Just
overlapping?
If you have two overlapping occurrences of x and u.
Let me show you the way it's done, basically, and it will be clear, actually. So how do we do this? So basically, you can construct a transducer mapping the original lattice into another lattice where sigma star is going to epsilon. The part that you're interested is going to itself, and again, sigma star is going to nothing. So now, yeah. Once you have this transduction, you can just project onto the output side. So you'll only have x, basically, with the correct scores. This is in the probability simmering, so everything is multiplied by 1, basically. So once you have the projection after the composition, you can just look at the weight of the particular string that you're looking for, which is the x part, and you have the answer. So this is the way it's done inside, and it's sort of interesting, so that's what is underlying. Now I'm going to show you how the back-off stuff is done. This was a problem when I remember first playing with FSMs when I was in CLSP, representing the back-off model in terms of finite state automata. And this required a change, basically, in the way the FSM composition classes composition is done. And the symbols here are the phi symbols, or the failure symbols. Basically, they are similar to the epsilon transitions, but in composition, they take the role of a rest symbol. So if you have an arc wi, you would take that arc, but if the wi, that particular wi is not there as an arc, you will take the phi transition. So that's the normal understanding of the back-off that we have. But as you can see, this is basically represented as exactly as the non-deterministic version of the same transducer would be, language model would be, but we have the back-off structure exactly now. So that's the fader class. And as you can see, basically, we have the bigram history here, and we're backing up to the unigram, and we can back off to the null history, and then take the WI. And these all will have their appropriate costs, of course.
And by the definition of P, this is now no longer non-deterministic.
Yeah. This is deterministic representation. And this we cannot use in the first pass, but it's good for risk scoring purposes, and it's exact. And this is probably familiar to most of you, the old perceptron algorithm. The inputs to the algorithm are the training examples, xi, yi, in our case, the utterances and the transcriptions. Initially, all the parameters are set to 0. And the algorithm will go over the examples, and for each iteration, it will calculate, given the current model, given the current parameters, and the feature counts computed from the utterance, and the path in the lattice. So gen x is the lattice, z is any path in the lattice, and we have the feature counts computed using the count algorithm that I just talked about. And there's a dot product with the parameter settings here. And the argmax is basically finding the best path. So zi is basically our current best path. And yi is the correct path, or the gold standard. What we do is we update the parameter value alpha by these count vectors for the correct.
yi is the correct transcription.
Correct transcription.
And
Let's call it gold standard.
And xi is what?
Xi is the utterance,
The acoustics.
the acoustics.
Oh, it's truly the acoustics.
Yeah, it is truly acoustics, but this is language modeling, actually. So I'm just giving you a very general sense of things. In reality, xi only comes into picture through gen xi. It just generates the lattice for us, and it gives the probability distribution. After that, it doesn't get into the picture.
That's because your phi of xy really depends only on y.
Phi of
Phi of x.
yes.
It only counts the n-grams.
Well, that is true. That is true, except for the baseline recognizer score. It has to be there, and the lattice itself, right? So the strings are defined in that way, all right? So, and then in the end, after a number of iterations, you have the alpha. One difference that we have in our algorithm actually is what is called a voted perceptron. Basically, we average the parameters after each iteration. So as you go, you don't overtrain as quickly as the normal perceptron algorithm will do. We have an averaging going on. Still, the perceptron is very bad in terms of generalization. It overtrains really fast. So you have to have a held out set in general. So in our specific training scenario, I just mentioned this. Yeah, go ahead.
The ultimate goal is to have a new language model score by
Yes. So the idea is this. I'll repeat this again. The idea is having a first pass lattice. We're going to intersect this lattice with a new finite state automaton. And the best path out of that one is going to be now our best hypothesis. And hopefully it will be better than what we would normally find through the first pass lattice. Okay, that is the idea. So it is a update in terms of the weights of an old model.
And you're calling it a discriminative language model because this new, what changes in the second transduction is the different n-grams get different weights, namely the alpha.
That is correct.
And so those weights get multiplied, the acoustic scores remain the same, and so now when you find the best path,
Right.
you're essentially changing only the language.
Yeah. And the first name for it was actually corrective, in the sense that it's correcting the mistakes of the first pass language model. But a general name is discriminative because it's discriminatively trained in some sense. And so the specific training scenario is basically once we have this model, what we're going to do is we'll scale the training lattice with the baseline recognizer weight. So you can think of this as having a zeroth feature, phi 0, which is equal to the recognizer weight, baseline recognizer weight. And the scaling factor for it is the alpha 0. So we just basically multiply all the weights with that scaling factor. And we intersect with the current model, which basically updates the new alphas. We give the contribution from the new alphas. And we have the usual FSM best path, choosing the best path from the lattice. And then now the correct utterance can be either the reference or, as I'm going to show, what we call the oracle hypothesis or the minimum error rate hypothesis in the lattice. instead of the reference itself, because the lattice might not contain the reference, basically. And if you're going towards this gold standard, we better make sure that it is in the lattice. And the algorithm basically increases the cost of n-gram features in the best path and decreases the cost of n-gram features in the correct path, or the gold standard. And if they're the same, actually, it doesn't do anything, really. So this is the basic algorithm. It's very, very simple. It only requires, the most expensive step, actually, is extracting the least cost path CI. Of course, the most expensive step of the whole algorithm is generating lattices themselves. Once they're there, it's just a matter of choosing the best path and then updating the weights. So it's cheap. And there's a small trick that you have to do. So now that we have this deterministic representation, if you have seen a trigram, now you have seen the bigram as well and the unigram as well. So there are 3 features firing at the same time. And normally, if this was a non-deterministic automaton, you would be visiting 3 paths. But since this is deterministic now, you're not going to be doing that. So you have to update the weights accordingly. So if you're going to take the trigram transition, you better include the bigram and unigram weights in there. And for bigram, you have to include the unigram weights in there. So by this construction, we still keep the deterministic representation, and we have the appropriate weights correctly computed.
So the C's are the
These are the
difference of the phi of the y minus the phi of the z that you had.
no, these are the alphas basically right here, right? So
These are the final alpha.
yeah. Yeah, except for symmetric changes maybe, but
Okay.
these are the
You could also
alphas.
say you could directly update this iteratively by updating just the.
Yeah, that's what's going on basically. You're constructing this as you go along. So this is basically doing also feature selection. I should mention that here maybe. I was going to do it later, but so when you're doing this, if the value of alpha was 0 and after the update it's non-zero, you have to add that into this. Into this FSM now. So if the arc wasn't there, and now you have found that that feature should be in your model, you add it. So the model grows as you see more and more evidence. So there are many questions. The first question was, well, what can we do to get it to work? One obvious thing was you should make the test data, training data, look as much as you can as the test data. Now, if you're generating lattices with a language model that is trained on the training data, and you're going to use these lattices of the training data, you're doing something wrong because you have seen these sentences, and clearly it's not the same as using the model on a different test data. So what we did was, for this experiment, was to generate partitions of the data and exclude certain portions of data when we're building the first pass language model. I'm going to explain it a little bit later on. But that's the idea behind this. So making the test data, the training data, look as much as we can as the test data. So what is the best gram and order? Do you want to use trigrams really, or bigram will suffice, or are unigrams doing the job? Do we really have to use lattices? Would n-best list work? This is also important when you want to move to non-finite state work, where you can only have a string input. Does it matter to use the oracle hypothesis, the minimum error rate hypothesis, or would reference transcriptions would be OK as well? And also, what if we have AM adaptation, acoustic model adaptation? Do we have to retrain everything, or is it OK just to use the unadapted model for our training? So these questions will be answered basically in a series of experiments. And these were all done on Switchboard, 2002 training and test sets. And we have about 3 million words, 276,000 utterances. And some of this was used as held out data because the perceptron algorithm is prone to overtrain. And we're evaluating the model after every pass over the training set on the held out and selecting the best performing model to control for overtraining. And we fixed the lattice score scale for a given run on this one. We did not learn it explicitly, basically. We tried and it didn't quite work. And there are reasons for it too. So the first set of results is keeping the training language model fixed. Basically, the language model includes all the examples in training set. And the alternative is removing certain portions of the training set. So if we're going to recognize one utterance, we make sure that that utterance was not seen when we were building the language model that is required to recognize that utterance. So we have 28 partitions of the data. Go ahead. No, we have 28 partitions basically. So for each partition, we exclude the data for that partition from the language model training data. We generate a language model. We use that to now recognize all the utterances in that partition. And those lattices are now used in the later stages of the algorithm. Okay? Baseline language model, well, it's a trigram cat's back of what we use for the evaluations, basically. It's nothing special. Sorry? Yeah, that's the baseline. Yeah, there's no cheating here, yeah. Baseline was around 39.2% error rate here. And as you can see, if you don't remove the training examples when you're building the lattices from the language model that creates these lattices, you get no improvement at all. And the X scale is the lattice scale, so this is the alpha 0, or the scaling factor for the lattice. And as you can see, basically, if you're using the you're in the ballpark for the lattice scale, you're OK. I mean, it doesn't really depend on it that much, unless you're using a wrong scale. And we're getting about 1% gain here. Actually, this best point gives 1.3% absolute in terms of word error rate. So this was one of the main things. And this was not done when we were first doing the experiments, when first Michael Collins tried this over 2 years ago. And that was the crucial, basically, win here. Second set of experiments, well, unigrams, bigrams, and unigrams, and trigrams, bigrams, unigrams. So unigrams get you half the way, almost half the way. Bigrams basically take you there. And trigrams, you can get an improvement, but it's not really too robust. But you can do it if it's cheap enough for you. And this has about 1 million parameters, by the way. I don't think it's on the slides here. So another experiment was comparing lattices with different n-best sizes. And as I said, this is important if you're going to do parsing, for example, or some complicated model that can only take a string as an input instead of the whole lattice. As you can see, 50 best, is not so good. But as you get to 1,000 best, basically, you have the same results as the lattice. So fortunately, our setup is such that we can do lattice as cheap as the n-best almost, except for processing time, of course. So it doesn't really matter. But it's good news in the sense that now we can try n-best based algorithms as well on it. And the fourth question was basically, well, should we use the reference or the oracle? And oracle seems to be better. So you basically find the minimum error rate path in the lattice and use that to guide your training. That becomes your gold standard. Sure.
So if you use the oracle,
yeah.
What is the lattice scale for the baseline system?
Lattice scale for the baseline, well, I mean, it's 1, basically. There's nothing really. So this is the...
Oh, you're talking about the scale of the lattice n-gram versus the new
Yeah.
one?
Yeah.
Oh, I see. And
why is the reference more dependent on it?
No. Why is the reference at 0.5 worse?
Well, I can tell you why, actually, but it's basically long utterances versus short utterances. You're never going to get to the reference, right? You always have errors if the reference is not in the lattice. So now that is more likely to happen in longer sentences, right? So you're kind of biasing yourself towards a subset of the training set. Because after a while, all you're learning is these things, these utterances that do not contain the reference. And
For a few iterations, the difference from the other is 0.
Yeah, these are driving you, and that's probably not a good idea. And why does it depend on the lattice scale? Well, the importance of the contribution depends on the lattice scale, right? If your initial model is more strong, basically, this die out, but if it's not strong enough, then they will stay there. So, well, this is just a summary of the results that I just discussed. So it's very important to control the training data. Trigrams and lattices are better, but not that much. And using the oracle best is a good idea. And now I'll briefly mention a set of experiments which has flavor of adaptation. here the idea is we have a large set of data, and we have another domain which is similar but not exactly the same that we want to adapt to. And this is nice because we have not seen the new data, and so we don't have to do this controlling the training data business here. And that's why we wanted to try out. We also want to see the effects of acoustic model adaptations. And we could also compare with map adaptation, maxima posteriori adaptation. And well, basically, one domain is the scan mail domain. This is a general voicemail system. And there's a smaller amount of data from this network center customer care line, which is different. So there's some gain to be obtained from language modeling. And actually, Michael and Brian has shown that it helps. And the amount of data is basically 17 hours of the new domain and about 100 hours of the old domain. And there's no change in either the lexicon or the dictionary for this set of experiments. And the adaptation is done in a supervised fashion. I'll just summarize the results. I'm not going to go into the details. So as it turns out, the perceptron alone actually is worse than the map adaptation method. And the reason actually is obvious. This model cannot correct or cannot choose a hypothesis that is not in the lattice. So it cannot correct for the mistakes that are done that don't show up in the lattice in the first place. So map is able to change the model and get you that improvement, but perceptron that uses risk scoring will not be able to get you there.
Meaning still map adaptation of the language.
Yeah, just the language model. We're not, yeah. AM adaptation is done with that.
So when you say map, you have the Dirichlet prior and the count?
Yeah, basically an interpolation of the new domain and the old domain. Yeah, that's exactly what it is. A Dirichlet prior, so that it's
So
linear basically.
New count plus
Yes.
alpha times
Yes.
new
Yes.
count divided by-
Yes. So it's the simple way of count merging, if you will. And well, as it turns out, the other two results are more interesting actually. So you can actually do adaptation and perceptron before adaptation and after adaptation. As it turns out, it's better to do it as early as possible because the adaptation also gains from the improvements in the language model. And if you do map, and on top of that you try this perceptron algorithm, you actually get another small gain. So you can improve the map results further. Actually, I don't want to spend too much time on this, but yeah. Basically, the idea is this can only correct for mistakes that appear in the lattice. So if your first pass language model is not giving you the opportunity to correct, it's not going to be able to do anything. That's the most important conclusion here. And the second one is essentially AM adaptation does not seem to hurt. The fact that the acoustic model is changing doesn't really affect. So yeah, the rest is more interesting, I think, so I'm just going to move forward. So I've been talking about these linear models, and I've given you an algorithm basically to estimate the parameters of these models using a very simple framework. Now I'm going to basically use the similar setup. Essentially, for the test, actually, it will be the same model, but I'll describe a different way of doing parameter estimation. What we're going to do is we will define a conditional distribution over the members of the Gen X space, the lattice, basically, for a given input X. And this is simply done by taking our linear model. So this is the dot product we had. This is the features of the linear model. These are the parameters. We exponentiate and renormalize. And the renormalization is done by summing over all the paths in the lattice. So this summation is quite easy to do. It's not the full space, and we're only going over the lattice. So this is just a matter of forward-backward. Actually, one forward pass. And now we have this conditional probability. And it's crucial that actually it's conditional because the input is not coming into the picture other than as a conditioner which comes into the picture only through the lattice. So the acoustic signal is not really in the picture. This is just a language model. So, and note that if you're just choosing the best path, essentially this is equivalent to using the linear model. So the weighted finite state automata implementation is exactly there. What we're doing is essentially giving a probabilistic interpretation of the same model. And this is exactly coincides with popular technique these days called conditional random fields. And I mean, you can name it in many different ways. It's a log linear model. It's an exponential model. But it's exactly the same thing, actually. And now what we're going to do is, of course, we're going to try to maximize likelihood, as we normally do. And here, though, it will be the conditional log likelihood. So it will be a discriminative model. So given the x, we're now trying to maximize the likelihood of the output y. So if you write down the likelihood, you have the linear model component here and a component that comes from the normalizer. And as it turns out, this by itself is not really a successful objective function because it tends to overtrain. And in the literature, there are many reasons for using this prior, but one way of looking at it is having a Gaussian, zero-mean Gaussian prior on parameters. And actually, on the SVM world, it has a different interpretation. But we can come up with a regularized objective function which adds a penalty on the parameters. So you don't want the parameters to get too large. So you don't want to emphasize the idiosyncrasies of the data. That's the basic idea around this, actually. And the value of sigma is typically estimated using held-out data. And it doesn't really matter what the exact value is. As long as you're in the ballpark, you're doing fine. And for this experiment, it was 2, I think. And well, 1/2 sigma squared was 2. And it doesn't really matter. Right? We tried a bunch of values, and it doesn't matter. But you can try deterministic annealing techniques and change the sigma and come up with other regularized objective functions. And so how is the optimization done? So here, basically, we can use different optimization algorithms that are based on generalization of the Maxent optimization algorithms. But as it turns out, it's much easier to use a general nonlinear optimization algorithm. And here, the objective function is convex, and there's a globally optimum solution. So we just go ahead and use a quasi-Newton method called limited memory variable metric method to optimize the regularized log likelihood. This method basically requires the function value and the gradient, and it will have an estimate of the second order, Hessian, basically. We'll try to estimate the Hessian as it goes along using this limited memory there. And we're using just a general implementation of this method. So in addition to the function value, we need to compute the gradient. And let's go back to the function value again and see what we have to do. So this part is very easy. This is exactly what we were doing with the linear model. The normalizer, and remember what the normalizer is doing, it's basically summing over the linear model's values over the lattice, right? So that's also rather easy to compute. And that is the function value. Oops. That is the function value. And of course, the parameter values give you the regularizer here. And now, how is the gradient computed? As it turns out, all you have to do is essentially compute the feature values. Remember, phi is the feature values for a particular training example. And then compute the expected. Now, the expectation is done over the current model values. Expected count of the feature values over the lattice. So again, the summation is over the lattice, so that is rather easy to do. And once you have these two parameters, this is again the regularizer component, you have the gradient itself. So actually, I'm going to explain how this is done using the finite state machine operations. Given the current model D, we need to compute for each utterance essentially a normalized lattice. So we scale the initial lattice with the value alpha 0, the lattice scale, and intersect with the current model. And then FSM push basically forms a probability distribution. It just renormalizes the lattice. And the function value is essentially given by the weight of this particular string that represents the gold standard for this utterance. And for each n-gram feature, we need the feature value, which is basically intersecting feature value for the correct utterance, which is basically finding the count using the intersected version with the current lattice, which is normalized. And then also this term, which is the model expectation, is also obtained by finding the general lattice's count. So given the feature wj, we have to first find the count using for the current correct gold standard, and also for the lattice. So those are the two counts that we need. And the zeroth feature, which is the baseline recognizer score, is given by the initial lattice. So you have that around as well. So given those computations, it's rather easy to actually have the setup so that we have the optimization done. The first set of experiments that we did investigate the use of regularization and also the effect of n-best versus lattices. So first of all, let's look at the baseline. This is 39.2. And we're reproducing the results for the perceptron algorithm here for n-best case and the lattice case. We also use the perceptron algorithm as a feature selection mechanism for us. So all the non-zero features that were found by the perceptron will be used in the CRF optimization. The features that have 0 for the perceptron algorithm will remain 0. So we are basically limiting the set of features using the perceptron algorithm first, and then using those initial values for the CRF optimization. This is done basically for efficiency reasons, and I'm going to give another set of features and compare these two. But this gives the base result basically. If you do not use a regularizer, after maybe 100 iterations, which don't seem to be doing anything, you start to diverge actually, and error rates start increasing. However, if you're using a regularizer, actually the sigma is 0.5 here, I was wrong. You basically get a further gain of 0.8% or so over the perceptron numbers. So the total gain from 39.2 to 37.4 or so is what we're getting, 1.8% absolute gain. And as promised, this is the comparison of the feature sets. So the perceptron result is around 37.8 here. And this is the curve that I have shown you, which gives you the perceptron features. So the parameters are also initialized by the perceptron training. And to contrast these, we basically went over the training lattices and found out what features actually are in the lattices. So just the frequency of the features. And we set a threshold on the frequency. So the frequency threshold, when it's set around 0.9, gives approximately the same number of parameters. So that's why this curve is there. And that number is around 1 million parameters. So there's about 1 million parameters in this model. And we also tried a larger model, which basically we decided on this number by looking at the memory that we could use and basically max the memory. That amounts to about 10 million parameters or so. And as you can see, basically the result is almost the same for these three methods. But the time that, the number of iterations that are required to get there are quite different. So the perceptron initialized model gets there in about 200 iterations or so, whereas it takes about 1,000 in the case where you use the frequency thresholding method. And it's much larger if the model is larger, actually. And also there are some local minimum, not local minima, but local issues that the Hessian estimator gets into, actually. If you have a larger window, this becomes more smooth. But these are the different feature selection methods that get you there. So in summary, well, OK, I mean, one question is, of course, is it worth doing? Well, you're getting 1.8% word error rate improvement. But now to do language modeling, you have to first recognize the training set. Well, if you're doing also acoustic model retraining and stuff, that might be worth doing. So for training, the most expensive part actually, once you have the lattices, is computing the objective function as gradient. But this can all be parallelized. Of course, the lattice generation can be parallelized as well. But when you're comparing with the perceptron algorithm, actually this parallelization is a big win. So if you have enough CPU that you can use, this might be a gain over the perceptron algorithm in the long run. And CRF parameter estimation yields improvement over the perceptron algorithm. And actually, you can use the perceptron algorithm to choose the features and improve the estimation using CRF parameter estimation. And it was clear that actually the perceptron algorithm is a better selector of features than just looking at the frequencies and getting there. And there are actually alternatives using, much like the maximum entropy feature induction methods, there are methods you can use with better features that are more discriminative in power. And so in conclusion, we've shown that discriminative n-gram modeling yields substantial improvements over the baseline system. It's very efficient to use. Basically, once you train it, it's very efficient to use because it's just another intersection and finding the best path over a lattice. So it has very little real-time cost. And although I have not talked about it, we have interest in call classification at AT&T. And as it turns out, the gains that we're getting here carry over to call classification. We get better outputs, and this actually results in better call classification. Improvements are additive to acoustic model adaptation techniques. So even though the acoustic model is changing, the corrective model that we're estimating here is able to give us some gains. And it has so far, well, we have tried on different internal tasks that I'm not reporting on here. It has worked well in every domain that we have investigated. And I want to actually give out some pointers to the software that we're using. You're familiar with the AT&T FSM library. You can also download it for research use on this HTTP address. And GRM library also is available now. That contains the GRM count that I was talking about. And Tau and PETC are very nice nonlinear optimization tools available from Argonne National Libraries, Argonne National Laboratories. And that concludes my talk, actually. All right. Thank you. No. As it turns out, OK, maybe I should, since we have time now, maybe I can say more there. So one question is, well, when should you start using this model? Should you recreate lattices at every stage of acoustic model adaptation? The answer is no, you don't need to do that. You can just do it over the first pass lattices, estimate a corrective language model, and use that along the line. And the earlier you use it, the better results are. And the reason behind that is your adaptation hypothesis is now better. So if you're doing unsupervised adaptation, you can actually start from a better point. So that's the answer. Yes?
Have you used this discriminative language model with the discriminative acoustic model? The results are additive?
Yes. All the switchboard experiments use MMI trained models. So yeah, they are additive. Actually, there are questions like, can we do this iteratively? Like, can we, improve the acoustic model, then language model, then the acoustic model? Well, we haven't really investigated that yet, but we might.
Did you try it for parsing?
Yes. Not me, but Brian and Michael did actually for parsing.
Michael's parsing?
Well, it's actually Brian's parser. And the story there is actually sort of interesting. The discriminative approach itself is not really helping, but together with the generative approach, it is not helping in the sense that it can get to the generative level, but not further. But if it's combined with the generative while doing the predictions inside the parser, it's actually improving. And this is actually a new paper that they wrote, so it might appear in ACL if it's accepted. So I know the story of it that way. Yes?
So going all the way back to how you incorporated the modified velocities to the FSM, so if you observe
That is correct.
Have you ever considered not doing that?
We haven't tried that out actually. As it turns out, this is easier for us. So since you get basically you can get the counts for all the n-grams in one pass. So instead of going through and saying that, okay, well, I have seen the trigram, so I should not have the bigram, it's easier to actually include all of them. So we have not considered that now. That is an interesting question. That basically, then you wouldn't have to do this adding of costs there when you're doing the non-deterministic deterministic representation, rather. But other than that, I don't know if it will be different. That's it. All right. Thank you very much. All right. Yeah. Go ahead.
In the first